Okay, thank you very much. My name is Han Heintjema. I have a bit of history in metrology, so I think I hope I can entertain you a bit with talking about some applications. But before I speak, I think it's a nice opportunity to let everybody of you do your own interferometric measurement of today. So I brought a little device, a box, Pandora's box. And of course, I forgot that also in my lectures, that in the pandemic it is very dangerous to pass through things. So please disinfect your hands before passing it through the next one. In here is a box. In here is... oh, wait a minute. Okay. In here is an optical flat, and I give you the opportunity to do an interferometric measurement of the flatness of this measurement phase, and then you have in once the most common application of interferometry in dimensional metrology, because every machinist will know how to do this, and I give you the opportunity to have this same experience. So go ahead. Then the question of today is, do you need glasses to see this interference pattern? Because we have a discussion of should you focus or not. So that's maybe something to think about. Okay. Of course, I'm the last speaker, so you will be waiting for the end. You will waiting for, yeah, somebody is nodding. Can you not skip something now? Maybe I can summarize bit 6. So we talked about holography and metrology, and I can notice the relationship is sometimes a bit uneasy. And maybe today, after today, it may improve because we have some entertaining lectures about. If you talk about multi-beam displacement interferometry, I must say it is displacement interferometry is a workhorse in dimensional metrology. So you see it all over the place. We saw something about Twyman Green. I think you can do similar things with Fizeau. And also flatness and ball inspection, it's an essential part of dimensional form measurements. And if you talk about interferometry and traceability, any length traceability in dimensional measurement is achieved by interferometry, somehow, sooner or later, in the end. And now, oh yeah. Okay, so I could say, okay, that's it. Here you have your applications. But I will give some personal perspectives, and it will have some overlap. So if you think, didn't I see that before? Yes, it's fine. It's not your fault. But today we celebrate interferometry, and we have to go back to one of the originators. Yeah. What? Oh yeah, yeah, of course. Oh, I'm so sorry. Yeah, good. Did you see something? Okay. Good. We go back to Michelson, and we all think Michelson's most important contribution is well, the special theory of relativity. But I think at least as important, if not more important for dimensional metrology, is his work relating the wavelengths of the red cadmium spectral line to the meter. And he published that work in 1894. He did it in a 200-page monograph in French. I did not read it, but maybe we can learn a lot of it, like the books of 20 years ago, maybe. For this, he achieved the Nobel Prize. What he did at that time, we see back a lot of things we heard of today. What did he do? Let me see. Oh, that's too quick. What he did do, he made a series of 9 etalons, the longest one was 10 centimeters because that was about the range of the cadmium line. And he made them smaller and smaller, up to 0.39 millimeters. And with that, he did magic things. What did he did? Oh shit! He did do two things basically. Here, he took one mirror. He achieved white light interferometry, and then he replaced this with this echelon. And at first, he took a very small distance. And that very small distance, then he displaced this echelon over this small distance until he found the same fractions of spectral lines. So he did two things. He did in fact counting interferometry. So he counted the lines. At least I must conclude he has counted this. And on the other side, he measured the kind of gauge block, which was now these two sides. So everything we do in dimensional metrology today, at least concerning the traceability, is covered in this. Because in the end, what did he do? He took his longest echelon. He took it of the 10 centimeters, and in part, he shifted it again and again, and then he replaced this one to this position, so he had the same line. And in parts, he measured in totally 1 meter. So in fact, he calibrated a line gauge, just what Mr. Flügge did. Mr. Michelson did the other way around, because now we measure the lengths in terms of wavelengths, but then he measured the wavelengths in terms of length. So basically what we have seen today, he did already right then. Okay, if you look what he used white light interferometry for absolute positioning. He did fringe counting for displacement measurement and line scale calibration, so he did both. And I think he must have counted the 1212 fringes in 0.39 millimeters. I can only conclude he must have done that in order to achieve what he did. And he, in fact, together with Mr. Benoit at the BRPM, he invented the method of exact fractions for absolute distance measurement, and that's what we still do with calibration of gauge blocks today. So his question was, how many fringes are there in a meter? And the reverse is that you can define the meter as so many fringes. But he was, I must say, he was ahead of his time. So at that time, people did not dare to redefine the meter in terms of wavelengths. It lasted until 1960, then the krypton line was measured. It was a bit better line. It lasted until 1983 when we have the lasers, which is mentioned, and the definition of the constancy of the speed of light, in which also Michelson had a major role. So today's practical implementation is that we have the meter based on wavelengths or frequency, if you like. So there are two. The previous speakers have, as I predicted, have said it already. But there are basically two traceability routes to all dimensions and size measurements of today. And the one is to have the absolute size in the gauge block size. Then you will see here today's gauge block. Interferometer, you have the method of exact fractions. That means you have this n, and then you have your length in terms of half wavelength. The other way goes through the wavelengths you use for displacement interferometry, which was also used by him already, but now, as Mr. Flügge has expected, we have more advanced interferometers, and also in that case, we just count the number, and we have also the length in terms of half wavelength. So that's our true routes to in which all dimensional metrology measurements are traceable to. And I will talk a bit about gauge blocks, also about the history. The gauge blocks are the basic standard of size for workshops and every dimensional laboratory. Here you see them a little bit. They are enabled both by the development of gauge blocks themselves, by Mr. Johansson, and also by the development of the gauge block interferometer by Custas and Zeiss about 1935. And you see here a nice lady, and I must say, I don't know if it is nature or nurture, but if you talk who is measuring the gauge blocks in the world, it's mostly ladies doing that work, also already in 1935. What you see here is the Zeiss gauge block interferometer. Okay. And what you see here on the wall is the schematic. You see here the barometer. You see here two rulers. One ruler is for calculating the exact fraction. The other ruler is for the relative humidity. You see here something which is the galvanometer measuring the temperature of the gauge block related to the mercury temperature. So all quite advanced and quite a lot of work. And on the wall you see the schematic, and I must say the schematic is also on the wall in my laboratory because it tells you everything about interferometry, about the Custas prism here. Here you look, here you have the gauge block. And what she is looking to is something like this. And really, if you stare in such an interferometer, you see something like this. And from this, you have determined in the length, you have determined a fraction. It is no fun. It is no fun. For us, it is fun today, but for that lady and for many people who worked in that, it was no fun. But if we look at that interferometer, I must say it was invented about 1936, and in Leuven we have one. I took a picture just before I left to show that I still have one. Wait a minute. Yeah, here you see the gauge block. It's over here. And what I found is a nice Prüfschein für das Thermometer. If I zoom in, it was made in Ilmenau in 1935. So you see here the Staatliches Prüfungsanstalt, 7 January 1935. And also interesting is if we talk about uncertainty and traceability, how they state. Here we see it is ohne, what did it say? Ohne wesentliche Fehler. Yeah, that's the result. So no 95% uncertainty, just only, so, okay. Okay, the other thing we see in the manual, I found back the manual, and somebody has scratched a bit in it, but we see here that's the uncertainty or the accuracy, whatever you like, absolute Messung. Sind zu einer Endmaßlange die Genauigkeit. Die Genauigkeit is 0.02 micrometer. Somebody has scratched a bit with pencil because he could not count the zeros, but here's 0.02 micrometer, and he said here, okay, it's micrometer. 0.02 micrometer in 1935, with a lot of effort. Then we think, that's a long time ago, and what has changed since then? So we have in the manual the accuracy. We have this lady taking big efforts to doing that. All kind of instruments we don't have anymore. And what kind of improvements did we make? Well, we have no more hand calculus, no more rulers, no more tables. We have a computer and we have an automated system. And fringe evaluation, not anymore by eye. I just showed you how difficult it is. We have no more spectral lamps. We have some spectral lamps, but we have now stabilized lasers, much better. And we have no more mercury in the laboratory because we don't like it. Because it's toxic. At that time, it was no problem. Especially not for ladies, maybe, I don't know. Everything is electronic. So what did we achieve? Then I look at today's CMC of some NMIs. And then I look at the Spanish one. Oh, that's too early. So 0.034 micrometer. Hey, that's a bit disappointing. The PTB 0.020. What has happened? SMD 0.18, 0.19. So what went wrong or what went right is the question. I think what went right is is, even if we may look down a bit on this lady and her hard work, we must say already that time it was an incredible achievement of that gauge block interferometer. On the other side, we may think, maybe this is greatly overestimated. Yeah, maybe we can do much better. Well, if we then now look at comparisons today, here's a comparison of a gauge block of 3 millimeters held in between 2018 and 2021, just before the pandemic. Then we see here the uncertainty and the deviations, and if you do the statistical uncertainty, you conclude, well, this is about what can be achieved, and even some laboratory are still ahead. So, despite all the progress, there are also things which have not changed so much. And the good news is still 20 nanometers for a length, even for a millimeter, as Peter said it, is not so bad. It's not so bad. It's enough for most dimensional measurement. So that's the good news. Okay, and once we have those gauge blocks, it's a lot of work. It's still a lot of work. And the dissemination goes to the next level gauge blocks, the lower gauge blocks, and they are used in the laboratory every day. And here you just see a collection. Oh, shit. A collection of boxes of gauge blocks which are ready to be calibrated by this, again, I must say, a lady, which has the patience of these, calibrating these one by one. So it's the big thing, it's a big industry. Every calibration laboratory does a lot of work of this. Then a question, what can you do more with a gauge block interferometer? Then I thought, I saw something about ball measurements this morning in the schedule. I said, okay, I once thought, okay, what can we do more with gauge block interferometer than just measurement of gauge blocks? Well, what you can also do is measure balls. If the ball is small enough, he will just fit under the gauge block. And if it is just, and then you need some piezos to make the gauge block exactly parallel to the flat. And then you have this optical scheme, and then you can measure the gauge block as if it is a gauge block, just you have a bit larger length by the ball. And then you may think, yeah, but you have a measurement force, you have indentation. Yeah, that's no problem. Then we just take a different gauge blocks. If it's twice as long, it has also twice the amount of weight. And we have, you can measure the indentation. And here you see our measurements of the indentation. And you can extrapolate to 0 force, and you have a nice calibration of the ball diameter. And the uncertainty which is delivered today is 0.03 micrometer. So it's not so bad at all. So it's one of the alternatives you can still do with a gauge block comparator. Then the other things, I must say, if you look in the world of dimensional metrology, there are two kinds of laboratories. The one does, they have one box of gauge blocks, and they do everything with it. They calibrate every instrument, whatever. The other type of laboratory, they bought a very expensive laser interferometer, and then they think, well, if I have such a thing, I must use it. So they try to do everything with laser interferometer. In laser interferometers, the previous speaker already mentioned, there are homodyne systems, heterodyne systems. The good thing is, in the end, they all count fringes, and they all have a fraction. And the manufacturer of the one type can exactly tell you what's wrong with the other type. But they both work. And to look a bit into what are the sensitive factors, I have here the display of one of the types. One of the types, and you can see here the length in millimeters. So you see here the resolution in nanometers. You see here what has to be input is the expansion coefficient, the air pressure, the air temperature, the relative humidity, and also the temperature of the thing you're measuring. It can be an instrument, it can be material. And in the end, out of this, computer, you hope it does do it okay. It's a kind of effective wavelengths, and you will recognize it's about the wavelengths of the red helium neon laser. So that's how it works. Then, how are these displacement laser interferometers used? They are, in fact, used in two ways. They're used indirectly to calibrate other instruments and standards. An example, it's also the big market, is calibration. I do it wrong again. Calibration of machine tools. Then these laser interferometers are called calibrators. And also the other thing is you can boost. Since 2 years, everybody knows what boosting is. You can boost. I was boosted the day before yesterday. Here we have a very old 1D length measuring machine, and even you have to read the scale in the old-fashioned way, but you can boost it using a laser interferometer, and then you can just read it. In fact, this is a quite old one. But then you can read your displacement in a traceable way. And what you see also in dimensional metrology, and you have seen it also in the presentation of Mr. Flügge, in dimensional metrology, you see two approaches. The one thing is to use the laser interferometer directly. And the other things, the other way is we use line scales, because if you use line scales, you do not need to bother about a bit of turbulence. It is rigid. It is there's no danger of that somebody puts his hand in a laser beam. Nothing happens. So there's in fact an indirect use of the line scales, because before they were used, the line scales were calibrated by interferometry. And just to tease Mr. Manske a little bit, I display here the 3D measuring machine based on laser interferometer. It was made by Mr. Ruil in 1999 at Philips. Maybe you will know. So it looks very much to the one used in Ilmenau now. And the other principle is used in the size F25, which was developed at the Eindhoven University by Mr. Vermeulen. So that's the two ways. And still those two ways, do we need materials or do we use laser beams? You can still see in some of the ISO standards, if you look at the acceptance test for CMMs, there's in fact two ways. The material way, you use some material, a gauge block or a step gauge or a bull bar, or you use the laser interferometer. These gauge blocks were calibrated before by interferometry. Step gauge, I will show you an example of how that was done. Bull bars are similar, can also be done by some way of interferometry. Then I will show you some tricks. If you don't have the money to buy a multi-beam interferometer, you want to do it with one. There are some tricks to bend the beam to compensate some errors. Here's some trick to do a line scale calibration, which does not satisfy the other principle, but by directing the beam such with a quarter wave plate so that it measures this distance once and the reference two times, and this beam subtracts this length once. Then if you have some rotary movement here, it exactly compensates the measurement along this line. I think I can call it the Eppenstein principle. It is very simple. And also here, a vision system, it's a commercially available vision system. It is this time also boosted by a laser interferometer. And altogether, with the vision system, you can measure the edges, and with the laser, you can measure the distances. Then another example is the calibration of laser of step gauges. Step gauges are also used in calibrating CMMs or other distance measuring instruments. Even calipers you can calibrate using a step gauge. Here you see a setup. It's a combination of a CMM and a laser interferometer system which uses here two flat mirrors, and because of these flat mirrors you can move the probe up and down and measure the next one without losing the signal. And the optical scheme is over here, and it comes down that you measure this distance 4 times, and in fact you effectively measured the mean of this distance, and that is exactly the position of your probe. So this is a way to compensate also for the other errors in one single interferometer, Mr. I can tell you. Okay. Then some other tricks. It's not so often done, but also laser interferometers are very good in dynamic calibration. Normally they can measure with a frequency of some 25 to 50 kilohertz. And if we make then an interferometer setup like this one, then we have here a plane mirror interferometer. The beam goes through the left side and to the right side. So altogether, we again calibrate according to the Abbe principle. And here we can, for example, calibrate the probe of a roughness measuring device. And roughness is also measured dynamically because the probe goes up and down all the time. And you can simulate this using this piezo, and then you can calibrate different things. So as the linearity, you can calibrate the bandwidth when the probe stops following this. You can check if parameters are calculated okay, and this is many things you can do. Systems are called moving table, and they're very versatile. You can do a lot of things with them. Then, talking about probe calibrations, this is another trick to have a folded beam, and in the end, the probe is calibrated also in a way that satisfies Abbe principle, because here you measure just the displacement as a sum of these two, and this is the reference beam, so you have even basically 0 path lengths different. And here is even the interferometer is put, there's a bit of air, it should not be there, it's better not, but in principle it's all compensated. And if you look at typical results at probe calibration at small distances using a laser interferometer, then this is a typical result, and then I come at one of the issues of interferometry, and that is the periodic errors. This is the calibration of a linear gauge, of an LVDT, an inductive probe, and you see small deviations with a period of a half wavelength, and that is typical for any interferometry system. And you don't want that, but I think there are several ways to deal with it, and the first way is just accept it. Yeah, it is that way. Because if you get such a result, you know it is an LVDT, there's no any reason why an LVDT would have this period, so you think, okay, this is the laser, and I put here the average, and this is my nonlinearity curve. I'm done, fine, no problem. It's different if you use this, for example, this displacement in a wafer stepper, then you're already wrong, you cannot do this. But if you just take measurement, it's not a problem. The second method is minimize it. Third method is correct it, and the fourth measurement is do something different. Okay, I will, but that something different also has to do in most cases with interferometry. So for correction, it was already mentioned by Mr. Flügge, the Heidemann correction. The principle is, as we saw in the very beginning, this morning, if you remember, the two phases of interferometry. You have two signals which are 90 degrees apart. If you display them against each other, they should form a circle. If they are not a circle, you have a little bit of the famous deviation. And if once you have done one circle and you have measured it, then you can conclude, oh, I'm so much wrong, I can do a correction. And there are some laser interferometers which have such a correcting system. And you can see here what happens if you measure with such a laser interferometer. First, it has a periodic deviation, then it finds out, hey, I should correct something. And after a few periods, it is more or less gone. If you find it not enough, then you can also go to a different method. And one of the different methods has also to do with interferometry, has everything to do with interferometry, is that you make a cavity. You make here a Fabry-Perot cavity. And advantage of a Fabry-Perot interferometer, it has much sharper fringes, so you can much more accurate, you can stabilize on very exact displacement. In this case, we have this cavity, and then we have this laser. We stabilize this laser on this cavity, and then we compare this laser with a stabilized laser, and then we measure the frequency difference. How do we measure a frequency difference? By letting them overlap. If you let them perfectly overlap, you have interference. Yes, there's the interferometer again. And you measure the frequency difference, and then you can relate this to a displacement. And I will save you the calculations, but you can easily achieve sub-nanometer resolutions. Why do you need such a large length? That is because if you make the length very short, you have extremely high frequencies to measure, which has different problems. So where you see interferometry, in this case, we have here 3 cavities in which interference takes place based on the Fabry-Perot interferometer. And you have here a Fabry-Perot interferometer, and you have also interference between the fringes here. So in this setup, we have 4 times interferometry, in fact. So interferometry all over the place. The other things, and I can say this very shortly because Mr. Fluke already talked about this. Also, I must say, I never did this myself, so I talk about things other persons did. Another possibility is the X-ray interferometer, or again interferometry. Again, you pass the limits of nonlinearity. Okay, I will not tell too much about this. Then other things you can do with interferometry. We have the famous or infamous angular optics. So you can also measure angles. We talk about dimensional metrology. What's in dimensional metrology? Displacement, angles, and a few things more. So this is the way to measure angles. Just to have here basic interferometer optics, and the angle you measure is the arc sine of the displacement divided by this baseline. Application are pitch and yaw of machine tools, flatness and straightness of objects, and flatness and straightness you can do by having a measurement base and then measure the variation in angle. And if you then integrate these differences, you can measure the straightness. If you do it in several lines and diagonals, you can measure for flatness, still flatness and straightness of mechanical objects. But I must honestly say, in this field, there's competition from autocalorimeters and electronic levels. So it's not all interferometry that shines. Sometimes there are some alternatives. And there's some tricky things. If you measure quite larger angles with this, you have an effect of this nonlinearity. So if you tilt it 5 degrees and then you press the 0 button on your laser interferometer, you will have some problems if you measure angles because of this nonlinearity. There are also other possibilities to measure angles using interferometry, and I must say, an overview was made a long time ago. If I press the correct button, yes. Long time ago, Mr. Jablonski made an overview, and I was very happy this morning to see one of his alternatives. Indeed, this is, I think, what Mr. Donchov showed. But he showed a lot of alternatives, a quite exotic arrangement for angle measurements. And I never saw anything of this applied, but I just show it. There are other possibilities if you have the patience and somewhere the money to do this. Mr. Jablonski told me, I'm not going to spend my life on these boring angular measurements, but it is still work to be done, probably. Then another thing, you will find it in any displacement interferometer box, is the possibility to do straightness measurements. The trick is here the Wollaston prism. You see here the Wollaston prism, it does a trick with polarization. If this moves up and down, you get a difference in path lengths. So you have a straight, and if you move this, ideally nothing happens. So with moving this, you can measure the straightness. You see it everywhere. I must tell you a small warning. The resolution in the straightness deviation is much worse than the resolution in the displacement. It's about 30 times worse. You have also a long-range option, and it's 300 times worse. So in fact, and you have a parasitic, if this angle changes a little bit, you have also a parasitic movement. So in the end, I don't think it's a very fantastic method, but okay, it's in the box that people use. And talking about straightness and flatness, we end up, why don't you measure straightness and flatness directly using a Fizeau interferometer? And I won't tell too much about it because it was already done this morning. I anticipated that. I just want to mention it is entering the shop floor quite slowly. This is in a dimensional, I found it in a dimensional calibration laboratory. They just bought it half a year ago. They got it second hand for €3,000. That was about the money they wanted to spend to measure flatness. Okay, what you typically find in Fizeau interferometers that you can measure flatness within a certain range, and as long as your surface is a bit optical. And what you see here is also typical, the fingerprint of the fringes which have been there. And also this has to do with the interpolation error I told you about. We do not see them in mechanical workshops so often, but okay, it is like that. And then this morning we had to talk about another, because in dimensional metrology we have different kinds of we have the displacement, we have the distance, but also we have the form deviations. The flatness we have just covered, but also another one is the roundness, or more in general, the sphericity. Sphericity can also well be done, in this case, with a Fizeau interferometer. This is, we did it some time ago, as you can see. This is, for your interest, this was a Muller-Wedel flatness interferometer. This here a reference surface, and here we have a reference ball of a CMM, 25 millimeters, typically. And we had a rotation measurement, and we designed something to have it in the right position to take interference, to take a flatness or a surface figure. And then we had to stitch it all together. It was quite a lot of work because you cannot, you can only cover a small part. But in the end, we achieved these kind of surface maps. In this case, peak valley 146 millimeter. We estimated the uncertainty by some Monte Carlo evaluations. It was about 20 nanometers, so not so bad. So with interferometry, you can also measure sphericity. What's the next form? The next form in dimensional metrology is the cylinder. The cylinder is a bit nasty thing also for mechanical measurements. Nobody likes to measure cylinders. This is the only example I found where a cylinder is measured using interferometry. And I must say, I didn't do it myself, I just repeat from the literature. But a cylindrical form was measured by, this is an hexagon. This is rotary symmetric. And then you get You get a phase grating, and then the first order interferes with the zero order. Also, it is rotary symmetric, so from all sides. And ideally, if your cylinder is perfect and everything is perfect, you see nothing. And if you see something, you see fringes. And from these fringes, with a lot of calculation, then you can calculate the cylindricity. So even cylindricity you can evaluate in once by an interferometry. It's not so easy. Also, I didn't see it so often. It was announced with big voice in 2001. I don't see them so often, but that can be. But just to show, even cylindricity you can measure with interferometry. And then we have, if you go smaller and smaller, I talked to you about flatness, roughness. If you go smaller and smaller, then we go to the microscopic interferometry. Surface mapping you can perfectly do. There are some limitation on angle, reflecting, roughness, but what I want to say now, you have sub-nanometer resolutions are possible. Then there are two types, the single wavelengths and the white light types. We can talk a long time. Mr. De Groot knows much more about it than I, so I will keep a bit silent. But the interferograms look a bit like this. If you have a single wavelength, if you have just white light, you can see some wavelengths, and then you have to scan, and you can put everything together, and you can measure any topography in this kind. In this time, a nice groove. And the daily work in the dimensional metrology lab. Is there any interferometry around? Even if you have just a box of gauge blocks, you do everything with it. Yes, in every dimensional laboratory, you see that the fringes, that the flatness of gauge blocks are checked with the optical flat. And if you look here, if you need eyeglasses or not, we still have to discuss. But okay, if you look here, you see fringes, and from that fringes, you can see if the gauge block is flat or not. And I don't know where my example is. Every mechanical engineer will also know how to calibrate a micrometer. Then it's important that the faces are flat and parallel, and even there are special optical flats are made for this, having special lengths so that all rotations are come along, all the four different positions come along, and you can still see if your micrometer operates well and if it is flat within limitations. And if you see the manual which comes with these optical flats, it within 5 lines it explains you all the principles on interferometry and gives you some examples or how many fringes you have and what that means for your flatness. So in fact, I should conclude that if we talk about applications of interferometry and dimensional metrology, I must say, interferometry is everywhere. And if you don't see it directly, it's still there behind the screens. And with that, I want to thank you for your attention.
Thank you very much for this very interesting talk. And are there still questions? I'm looking onto the moving fringes.
Yeah.
So if it's not the case, thank you very much again.
Oh, this is great. Great. Yeah, thank you. Thank you.
The T-shirt too.